Actually, this fact is quite evident from the following diagram. Where I have drawn a pair of axes, let us call them x and y, and I plot the points on the plane corresponding to the two ordered pairs 1 comma 2 and 2 comma 1. 1 comma 2 would be a point with an x coordinate of unity and a y coordinate of 2. So, if this is 1 and this is 2, 3, so forth, 1, 2, etc., then the first point 1 comma 2 would be around here. The second point 2 comma 1 by the same procedure would land up here, and these two are obviously different points on the plane. Since our signals are supposed to be functions which have different values at different points of the domain, and since both these two are clearly different or distinct points of the domain, there is no reason at all why a signal should have the same value at the first point and at the second point. In short, therefore, we mean to exclude the possibility of confusion and consider the most general situation by making a distinction between the points 1 comma 2 on the one hand and 2 comma 1 on the other hand, or more generally the point A comma B on the one hand and B comma A on the other hand. These are always different points. There is one more occasion in which we will be concerned with ordered pairs of numbers, and that is about to be discussed in a moment. But let me wind up my remarks about the domain of a signal by saying that here we have considered a domain of 2 dimensions. We could also consider a domain of 3 or more dimensions and define signals on domains of higher dimension. Such signals where the domain is not a point on a line, but either a point on a plane or a point in 3-dimensional or higher dimensional space is called a multi-dimensional signal. Multi-dimensional signal. A picture such as a photograph, for example, is an example of a multi-dimensional signal, because at each point on the surface of the photograph you have a certain color value or gray level value depending upon whether the picture is color or black and white. And since the points on a picture, the points on the photograph constitute a subset of the points on a plane, this is an instance of a 2-dimensional domain, and therefore, the picture is a 2-dimensional signal, a multi-dimensional signal. You could correspondingly have 3-dimensional signals. For example, suppose you are in a room, consider different points of space in the room. Each point of space in the room could have a different temperature at a given point of time. Points closer to the roof in summer would have a higher temperature than points closer to the floor. This is just a fact that everybody knows. And so, if we define a signal as the function that takes every point in the room, in the volume of the room, to a value equal to the temperature at that point at a given instant of time, this is a 3-dimensional signal, a signal whose domain has 3 dimensions. So, signals can be 1-dimensional or multi-dimensional, and both these terms refer to the dimension of the domain of the signal. Now, moving on, we will now talk about the range of a signal. The range of a signal is the set out of which the signal takes values. The temperature at a point in a room is a number which has the units of degrees centigrade or degrees Kelvin, whatever. Now, this is a member of a certain set which we call the domain, the range set. The range set therefore contains all possible values that the given signal can take at different points on the domain, the set of all possible values that the function can assume. Thus, for example, if we take a concrete instance such as the signal sine theta. Theta now is the domain, and we know what principal values theta can take. Theta, the domains, the set of all values theta is the interval 0 to 2 pi on the set of real numbers. What about the range of sine theta? The range of sine theta is the set of all values that sine theta can assume when theta runs from 0 to 2 pi. This we know is the set -1 to 1. In short, if theta lies in the range 0 to 2 pi, then sine theta lies in this set. This is the range of a set. In general, the range of a set for the kind of instances we will be considering in this course will be the set of real numbers, and therefore, we would denote the range by this symbol. But for mathematical considerations which cannot be fully explained at this early stage, it is more convenient for us to consider a larger set than the set of real numbers, and we actually choose the set of complex numbers denoted by C, complex numbers. Now, I would quickly like to go through a review of complex numbers. Complex numbers, as we know, are represented by ordered pairs of real numbers. We are back to ordered pairs once again, as you can see. And so, a general complex number C would be written as A plus I B, where I is the square root of -1, something we know. Somehow, for historical reasons, in electrical engineering, the letter I has been used for other purposes than representing the square root of -1, and in electrical engineering, instead of I we use J. Square root of -1. So, it is the same thing, the name alone is different. So, we would write C as equal to A plus J B. A is called the real part and is denoted by the real part of C. B is called the imaginary part and is denoted by this. Okay. So, this is the real and imaginary part representation of a complex number. Since a complex number is also an ordered pair, any complex number would be represented as a point on a plane. If we use the horizontal axis to denote the real part of any complex number x and the vertical axis to represent the imaginary part of the same complex number, then A plus j b would be say a point over here, where this would be A and this would be B. Different complex numbers would result from using different values for A and B, and again it is evident that A plus j b is certainly not equal to B plus j a. They are different complex numbers. So, the order matters. What we have just plotted is often called the rectangular representation of a complex number. There is another way in which complex numbers can be represented, and that is in polar coordinates, and we can do that to get the polar representation of a complex number. In a polar representation, we convert A and B into polar coordinates using the equations r equal to the square root of a squared plus b squared and theta equals tan inverse b by a. Clearly, A and B can be recovered from r and theta, and that can be done by using the equations A equals r cos theta, B equals r sin theta. Anyway, all this is by review, by way of a review. You already know all of this. Now, using r and theta, we could represent points on the plane, but now the coordinate frame would look a little different. I would just draw a horizontal line like this. This is the r direction, and the theta direction would be an arc in this form. Any point, let us say the same point A B plotted alongside, would now lie somewhere over here. Its location on the plane would not change, but it would now be represented by two numbers, namely this angle, which is theta, and this length, the length of this radial line, which is r. So, this r and theta would be given by this equation as well as this equation for r and theta given below. So, you could use either the polar coordinate system, the polar representation, or the rectangular representation to represent complex numbers, to address a particular complex number. And there are times when using one is more advantageous than using the other. This is the point we will just be coming to now. When you want to add two complex numbers, you would find the rectangular coordinate representation more convenient, because C plus C prime is defined as A plus A prime plus J B plus B prime, where of course C equals one second. A plus J B and C prime equals A prime plus J B prime. So, this is how we define addition. and clearly it is very easy to add two complex numbers if they are in rectangular coordinates. Subtraction is no different from addition really, except that c prime is replaced by minus c prime. Minus c prime is defined as minus a prime minus j b prime. This is the first stage of defining subtraction, and subsequent to this we will say that c minus c prime is simply c added to minus c prime. No big deal. Clearly, subtraction is also easier to do if we use rectangular coordinates. Coming to multiplication and division, the scene is a little different. Multiplication, here it is not convenient to use the rectangular representation, because if we use the rectangular representation we would get c times c prime as equal to a b minus a prime b prime plus j times a prime b plus b prime a. That is not so convenient. Instead, if we look at multiplication in polar coordinates, it is much easier. Let us say that c is r at an angle theta. This is how we would denote the function in polar coordinates, and c prime equals r prime at the angle theta prime. Then the multiplication of c and c prime is given by r times r prime at an angle theta plus theta prime. Likewise, division is very straightforward in polar coordinates. C divided by c prime is simply given by r divided by r prime. The usual proviso that r prime is not 0 must be fulfilled. The angle of this is given by theta minus theta prime. So, this summarizes the four things we normally do with complex numbers: addition, multiplication, subtraction and division. And you see that for addition and subtraction, the rectangular coordinate system is more convenient. Multiplication and division, the polar coordinate representation is much more convenient. However, there are a couple of other things we do with complex numbers, and as it happens in the study of signals and systems, we will be doing this pretty often. And these things are raising complex numbers to a power or extracting the nth root. Nth roots of a complex number. And for this it is important to just use the rules of division and multiplication that we have already devised. So, how do we raise a certain complex number, say c to the power n? Recognize that c to the power n is nothing but c times c times itself n times. it has to be multiplied with itself n times, and therefore, c to the power n is just equal to, in polar coordinates, r to the power n at an angle n theta, where of course, c is n theta, c is r theta. Extracting the nth root, now this is more dangerous, it is a little complicated, because unlike c to the power n, which is a unique number, if you extract the nth root of c, denoted by this, then from our knowledge of algebra we should expect not one nth root, but n nth roots. So, there are n solutions to the nth root of c. So, how do we find the n different nth roots? Let us try to understand this carefully. We have c given again, just to remind ourselves, by r and theta, fine. Now, we want to find a number, let us call it d, such that d to the power n equals c. Since we have just seen how to raise a number to a power in the earlier lines, we can immediately see that one of the nth roots is very easy to find. What is that one of the nth roots that is most easy to find? It is simply d equals the nth root of r, that is the magnitude of d, the length of the radial vector of d, that is clearly just extracting the nth root of a real number, that is straightforward. Now, there is the angle, and we could always take this angle to be theta by n. But then what about the nth root of r? The nth root of r, in this case we will only choose the positive number, which is the nth root of r. We are not concerned with complex numbers or negative numbers at this stage, because we know that if this nth root of r has to represent the magnitude of a complex number, then since the magnitude of a complex number is always positive or at least non-negative, this has to be the non-negative root of d, non-negative nth root of d, and finding theta by n also should be no problem. However, this is just one of the n different nth roots of c. What about the remaining roots? In order to understand how we find the remaining roots, let us first plot c on the complex plane. Let us say this is the origin, this is the positive direction, the radial direction, and let us say that c is over here. This is the point c. Now, you see what we have just obtained as the nth root of r with a phase or angle equal to theta by n is one of the roots, It is the most straightforward root. It is obtained by just taking this radial vector, finding its nth square root, and then taking this entire angle and dividing it into n equal parts. So, you would get a much shorter vector normally, assuming that r is greater than 1, and you would get a much smaller angle. But because of the fact that theta plus 2 pi is also equal to theta, you have a means of extracting more roots. What we will essentially do now is to see how we get the remaining roots. Can you break here for a minute? So, let us say D equals S at an angle phi. D equals S at an angle phi. Our task is now to find out what is S and what is phi. Okay. Now, remember that S, which is the magnitude of D, quite like the magnitude of C, which is R, has to be a positive number, and therefore, from D to the power n equals C, we already know that S to the power n must be equal to R, and therefore, S is nothing but the positive nth root of R. There is only one positive nth root of R, and we can easily find that out. So much for S. Now, for phi. What value can we give to phi? The straightforward answer is take phi equal to theta by n. This of course, is one of the correct answers, but it unfortunately leaves out the remaining correct answers. If phi is chosen to be theta by n, then clearly n phi is theta, and this particular choice of phi and S would clearly give us one of the nth roots of R of C as follows: D equals the nth positive root, the positive nth root of R at an angle theta by n. Now, we have to look for the remaining n minus 1 roots, and these can be found as follows. There is little we can do with the magnitude, because S has to remain the positive nth root of R. However, there is room to play with the angle of D, namely phi. We have just chosen phi to be theta by n. Are there other values of phi which will, when multiplied by n, yield the same value as theta? On the face of it, it seems impossible, but we must recall that angle in a polar representation repeats itself every 2 pi radians. In short, theta is the same as theta plus 2 pi. In fact, it is the same as theta plus 2 k pi for various values of k. Once we recall this, we can see a means of extracting the remaining roots of C by finding other values for phi. We will now see that we can take, we will call the first value of phi that we have found, phi equal to theta by n, as phi 1. Now, we can say that phi 2 is just theta plus 2 pi, the entire thing divided by n. which means phi 2 equals theta by n plus 2 pi by n. Now, this quantity theta by n plus 2 pi by n is quite certain to be different from theta by n, because we have another angle 2 pi by n added to it. But what happens is that when we multiply phi 2 by n, we will get n phi 2 equals theta plus 2 pi, which comes out to be the same angle as before. Thus, phi 2 is another legitimate angle that can be assigned to the nth root of C, or equivalently to the another choice for D, for the angle of D. Now, we can clearly see how we can get more values for phi. Phi 3 could be taken as theta plus 4 pi by n, and so on until we come to phi n equals theta plus n minus 1 times 2 pi by n. Each of these gives us different values for phi, and we would say that the nth roots of C may be enumerated as S phi 1, S phi 2, and so on until S phi n. So, there are n nth roots of the complex number C. In general, most of these would be complex, but there could be certain specific instances where the choice of n or the choice of C could yield more than one real root. That, I think, summarizes what we need to know about the theory of complex numbers, as we will be using in signal and system theory. The last thing I would just like to touch upon relating to complex numbers is how we have complex valued functions, how we represent complex valued functions. A complex valued function is a function whose value at each point in the domain is a complex number. So, the complex valued function can take complex values at different points of the domain, and adding two complex valued functions would require you to add the values at corresponding points and therefore add complex numbers. You would similarly require to multiply complex numbers sometimes, and so on. This was the reason for the brief review that we just did. This was of course the instance where we have chosen the range to be the set of complex numbers. There could be situations where we want a more intricate set for the range of our signal. Just like for the case of the domain, we started with a one dimensional domain, namely the set R or the set Z, which was the set of integers. We could use a higher dimensional range. This we would have to use where the functions we want to represent are actually more complex quantities than just complex numbers. What can be more complex than complex numbers? Well, here are a few examples of signals where we want to have a more intricate representation than is possible with just a one dimensional complex range. The most common thing that comes to mind is how we represent values of a color image. a color picture is one which has different colors at different points on the surface of the picture. Now, while it is out of the scope of this course to discuss this in depth, it can be shown that in order to represent different values of color, or rather to distinguish different colors, we need a representation that goes beyond just the set of complex numbers. What is most frequently used is not the set of complex numbers, but a three-dimensional real number set. That is, we use R3 to denote different values of color. This follows from some theory of color representation, which was done quite some time ago, which showed that human vision can be represented by a set of values called the tri-stimulus values of any color. This theory says that if you want to reproduce any natural color that you observe with your eyes, then you only need to mix appropriate quantities of 3 so called basis colors or basic colors. Very frequently we use basic colors as red, blue and these are chosen as the basic colors. So, any color that you can see with your eyes would be represented by a certain combination, a certain proportion of red, blue and green. This therefore means that in order to label a color properly, in order to represent a color accurately, we need to specify 3 numbers. The 3 numbers would essentially be the amount of red, the amount of blue and the amount of green that have gone into making that color. Thus, a color value would actually be a 3-dimensional vector consisting of the quantities R, G and B. And such 3-dimensional vectors we know are elements of R3. Thus, in the case of representing color pictures as signals, we find that the domain is 2-dimensional it is R2 and the range is R3. Functions or signals where the range is more than 1-dimensional are said to be multivariate. Multivariate functions, the first example of which we have seen as color pictures, can be many more. We can find many more examples for them. For example, let us say the direction of air currents at different points in a room. So, different points in a room constitute points in R3. So, for example, air currents room would have a domain, as I just said, of R3, because the room is a volume of space, and at each point on the domain, which means to say at each point in the room, we would actually have to represent the direction of the currents. That means, we would have to give two angles to give the direction of the air current at that point. If we wanted the magnitude as well as the direction of air current, then we would actually have to give the x component, the y component as well as the z component of the air current magnitude at each point. Functions where the range of the signal requires more than one dimension for representation are called multivariate functions. Now, the color picture is one instance of a multivariate function. We can think of more examples. Consider, for example, air currents at different points in the volume of a room. Suppose we wish to represent this as a signal. That means, at each point within the volume of a room, we would like to know the magnitude and direction of the air currents. Now, the magnitude and direction of the air currents is essentially the magnitude and direction of the velocity of air at different points. For example, close to the ceiling fan, you would have a lot of air current magnitudes, mostly aiming downwards. At other points, you could have different air currents depending upon local conditions and all kinds of circumstances. So, to represent air currents in a room, you would need a three-dimensional domain. Simply because the volume of the room is three-dimensional, you would also require a three-dimensional range. And this three-dimensional range would simply be used to represent the three velocity components along x, y and z of the air current at the respective point on the domain. So, at each point on the domain, at each point in the volume of the room, we would have to place a three-dimensional real vector. So, this is another case of a multivariate function. We can construct various multivariate functions in the same manner. For example, another example is the magnitude and direction of the Earth's magnetic field at various points on the Earth's surface. Now, the Earth's surface is a sphere. So, maybe it is a little confusing to understand what the domain is, what is the dimension of the domain. Now, though it is spherical and not a flat plane, it is quite clear that to identify a specific point on the Earth's surface, we need two numbers, namely the latitude and the longitude. And latitude and longitude are both real quantities. So, the domain becomes two dimensional, one for latitude, one for longitude. The range is another question. Here we want to represent the magnitude and direction of the Earth's magnetic field. If we assume that the Earth's magnetic field is confined to the horizontal plane at each point on the surface, then we only have to give the direction of the magnetic field as so much component in the northern direction, so much component in the eastern direction or western direction, whatever, and this is all we would require to do. If therefore, we assumed that the magnetic field is confined to the horizontal plane, something which is certainly not strictly true, then we would simply have a range which is also two dimensional. For this course, we will confine ourselves to the simplest kinds of signals, signals which have a one dimensional domain and a one dimensional complex range. So, for the rest of this course, the domain we will assume is either R or the set of integers z, that the latter is for discrete signals, signals defined on what are called discrete time. I will come to that in a moment. The range in both cases will just be the set of complex numbers. We do not have to worry about multivariate multidimensional signals in such an early course, but I did have to mention them just to tell you that there are more complex signals possible, and that almost any phenomenon that one can think of can be represented as a signal. Right. So, we have multidimensional and multivariate signals, and signals can be represented as maps from domains to range.